All right, welcome everybody to our online lecture for today, March 27th. So let's get into what we covered on Monday. Just get my timer started here. All right, so on Monday, we looked at Ka and Kb. All right, so remember these are equilibrium constants, Kq, but for acid and base. Same thing though, products over reactants. And we talked about this idea of strong. So a strong acid dissociates 100%, ionizes, breaks down 100%. A weak acid doesn't. So it breaks down less than 100%. Then we have strong electrolyte and weak electrolyte. So a strong acid is a strong electrolyte. Same with a base. Remember, an electrolyte is an ion in water. A weak acid or a weak base is a weak electrolyte. Then we looked at problem 76A as long as talking with section 17.5, which is water. So remember, water is called amphoteric. It is both an acid and a base, depending on what it's interacting with. Water can also auto-ionize. That is, when it reacts with itself, it will create H3O plus and OH minus. If we do the equilibrium constant for that, then we have Kw equals H3O plus multiplied by OH minus. At 25C, this equilibrium constant Kw is equal to 1.00 times 10 to the minus 14. And that allows us to understand what neutral pH means. Neutral pH is 7, and neutral means acid concentration equals your base concentration. And if you're at 25, that concentration is times 10 to the minus 7. So in 76, we use Kw to calculate either OH minus or H3O plus concentrations. And we have to say if the solution was an acid or a base. Remember, if you have more H3O plus, you're an acid, more OH minus, you're a base. From there, we went on to pH. Whenever we see the lowercase p mathematically in chemistry, that always means minus log. So pH is minus log H3O plus. And pH, if it's below 7, it's acidic. If it's above 7, it's basic. And then we have the relationship pH plus POH equals 14. We can also calculate POH. It's just minus log OH concentration, and it's the opposite of pH. And so what if we're given a pH or a pH? How do we calculate the actual concentrations? You do 10 to the power of like negative pH or 10 to the power of negative POH. Also, remember pH is a logarithmic scale. That is, every time you, so I actually drew it wrong. I should go 3 to 2 to 1. As your numbers drop by 1, you are 10 times more acidic. And so a pH of 1 is 100 times more acidic than a pH of 3. And then we ended on 76A, which we use this information to we were given a concentration. We have to find pH and POH and then determine if we're acidic or basic. And we're actually going to start with 76, and I'm going to stop my sharing so I can share my whole screen here because I'll be jumping back and forth. So let's share the screen. All right. So let me just get my Excel open. Fantastic. All right. So we want Canva. That's what we want. And we are going to look at 78D. So 78D says, along with 78, calculate pH, POH, and determine if this is acid or base. Here, we are giving OH minus concentration, which is 5.4 times 10 to the minus 5 molar. Now, the reason why I want to bring up 78D is I want you to be careful to know what you're calculating. Here, if I do minus log of this concentration, what I'm actually calculating is a POH. So if we do that calculation, minus log 5.4 times 10 to the minus 5, POH is 4.27, which means pH is 14 minus 4.27. Remember, pH plus POH equals 14. So we do 14 minus that, 9.73. Our pH is 9.73. So our pH is above 7, so this is a basic solution. So I just wanted to bring up that problem there, but let us move on with our lecture. There we go. All right. So the next thing we are going to talk about is how to calculate pH from a strong acid. Okay. And remember, a strong acid dissociates 100%. So 79A says we have 0.25 molar hydrochloric acid. And I want to know what is the pH of this solution. So your first step should be to write your acid with water. So normally in class, I would have you do this for a minute. So if you'd be so kind, pause the video, try it out. All right, so HCl is an acid. Remember, acids donate a hydrogen to our base. So we have Cl minus. That's our, so let's do some nomenclature. Acid, base. This would be our conjugate base, right? The acid makes a conjugate base plus H3O plus. This is our conjugate acid. Right, so there is our equation. Now, I want to know what pH is. Remember, pH is minus log H3O plus concentration. So what I'm really asking is, what is my concentration of H3O plus? And we could set up an ice table if we wanted to. We don't need to, but we could. So I'm going to do that just to show this concept. Let me put my state symbols, AQ, liquid, AQ, AQ. Let's also write RKA, our acid equilibrium constant, Cl minus multiplied by H3O plus. That's all going to be over HCl. Now, water is a liquid, so we don't put it in our Ka. We also don't care about it in the ice table, so get out of here, you liquid. All right, HCl, what's our initial concentration? 0.25. No chlorine, no water. We can calculate Q. Remember, Q is just initial concentration, so, or any concentration that's not equilibrium. 0 times 0 divided by 0.25. Q is 0. So if Q is 0, we have to make products. So minus X plus X plus X, then minus 25 minus X, X, X. All right, so we've come across this before. Now we have to figure out what X is. And before, when we've done that, we've always plugged it back into Ka and solved from there. However, in 79, I actually don't give you Ka. So we have to use our definition of strong acid. A strong acid breaks down completely, which means that at equilibrium, I will not have any HCl left. So my ice table, 0.25 minus X equals 0. Remember, I plus C equals E. Well, that means X is 0.25. So everywhere I have an X, I have a 0.25. So at equilibrium, my H3O plus concentration is 0.25. Remember, we need that because I want to figure out pH of this strong acid solution. And pH is minus log H3O plus. So now I know that. So let's figure out pH. pH equals minus log of 0.25. And so the pH is 0.60. Now I just forgot the number. 602. That is your pH. So that is how you figure out the pH of a strong acid solution. Now, let's do one more. If you were to look at the notes, you would find that problem 79 has 3 problems. We are going to actually do 79C. This is another one of those problems where if you'd be so kind to try it on your own before looking at the solution here. So, pause the video, see how far you can get with 79C. And in case you don't have the PowerPoint, this is what it says. You have a solution that, and whenever I say like solution, that's going to be meaning you're adding this to water. You have a solution that is 0.052 molar HBr. That's a strong acid. And 0.020 molar HNO3, also a strong acid. So I want to know what the pH is. So the first thing we need to do, you don't need to, but it's always helpful, write the chemical equation. And so I'll do that for each strong acid individually. So HBr plus H2O. So acid gives hydrogen there, makes Br minus plus H3O plus. So that's my first acid reaction. My second acid reaction, HNO3 plus H2O, goes to NO3 minus plus H3O plus. And if you are wondering about these charge symbols, again, remember a hydrogen is a +1 charge. So HBr, when I lost a hydrogen, that's why it becomes Br minus. H2O, when I gain a hydrogen, I gain a plus charge, become H3O plus. Now, these are happening in the same beaker, so I could combine them. You don't have to, but you could. And what I want to point out is that these strong acids are acting independently of each other. Right? HBr and HNO3, they don't care that they're in the same beaker together. They're working independently. And so a strong acid means, okay, I'm dissociating completely. So from HBr, the amount of hydronium I created is how much HBr I started with, 0.052 molar. HNO3, the amount of hydronium I have is 0.020. And this is all in the same beaker. So the total amount of H3O plus I have is 0.020 plus 0.052, which is 0.072 molar. And then I want to get the pH of this, which is 0.072. So pH is 1.14. So the main takeaway from this problem is that strong acids dissociate completely, right? And when I had multiple strong acids, they work together. All right, so with that, we are going to move on to the material that we had planned for today. Let me just open it here. All righty. So what we want to talk about now is the pH of a weak acid. All right. So sorry, just a little technical difficulties on trying to do multiple things. There we go. Sorry, I'm working on a tablet as my other screen. So let's go back to Canva. So we just did the pH of a strong acid. So the next thing we want to do is the pH of a weak acid. Remember, a weak acid doesn't dissociate 100%. Does not do that. And I'm just going to jump into a question. On the slides, it explains how to do this. I think it makes a lot more sense if I explain the steps while doing the question. So question 80. I have a 0.250 molar hydrofluoric acid solution. I want to know what is pH of this solution. And we are also given the Ka of HF equals 6.8 times 10 to the minus 4 molar. All right, so whenever we're dealing with an acid, the first thing we want to do is write the equation. Oops, don't know how to spell right. Write the equation with water. So we have HF plus H2O. So here, remember the acid gives hydrogen to the water. We make H3O plus F minus. We want state symbols because state symbols are important here. Liquid. We can write our Ka expression, right? Products over reactants. So H3O plus multiplied by F minus divided by HF. All right. Now the question is, since we're dealing with pH, and again, I'll write it down. I'm going to keep reminding you of this. pH equals minus log H3O plus. So again, I need to find H3O plus at equilibrium. So let's set up our ice table like we did in the strong acid situation. Again, liquids, we don't care about those. The amount of HF we have is 0.250. H3O is 0. F is 0. Let's calculate our Q. Initially, we have no hydronium, no fluoride. HF is 0.250. So Q equals 0. So we need to make products. So minus X plus X plus X. 0.250 minus X, X, X. So we're in the same situation we were for the strong acid. The difference is the definition. This is a weak acid. Weak acids do not dissociate 100%. So I don't know what X is. So I need to solve for X like I've done the other examples in the ice table. I need to plug my E. I need to plug my E row into Ka. Now, before we do that, remember, when we have a minus x or a plus x situation, we always want to check the x is small approximation, because otherwise we would probably have to do the quadratic, if not something more complicated. So I want to avoid that. So my Ka is 6.8 times 10 to the minus 4. Remember, to check the x's small approximation, you take your equilibrium constant multiplied by 100, which is 6.8 times 10 to the minus 2, which is 0.068. This is smaller than my initial concentration. So what I can assume is that this minus x term is insignificant. It's not going to matter in my calculation. So at equilibrium, our concentration is 0.25. All right, so let's solve for x now. Remember, we need to plug in the Ka. So Ka, we have that value, is 6.8 times 10 to the minus 4. That is equal to H3O plus is x times F minus, which is x. Remember, these are equilibrium concentrations, divided by 0.250. All right, so I need to multiply each side. Oops, sorry, not used to not having a touch screen here. I need to multiply each side by 0.250. So when I do that, pull up my calculator. Come on. There we go. 6.8 times 10 to the minus 4 times 0.250. We have 1.7 times 10 to the minus 4 equals x squared. X times x is x squared. Square root each side. X equals 0.013 molar. X equals 0.0130 molar. All right. And remember, that's my equilibrium concentration of H3O plus, but I want the pH. So pH equals minus log H3O plus. So if H3O plus is 0.0130, pH equals minus log of 0.0130. So pH for this solution is 1.88. All right. So take home message from our last two problems. So for a strong acid, and this also works for bases, strong acid or base, the amount of H3O plus or OH minus, if it's a base you make, is your initial concentration, because it breaks down is initial concentration, because your substance breaks down 100%. In a weak acid or base, you need to do an ice table. And how do you know if you have a weak versus strong acid? Well, easy. If I give you a Ka, it has to be a weak acid, right? Strong acids don't have Kas. Now, there is another problem there, 80B. So this I will let you use for practice. If you want to check your answers with me, I am happy to do that. But 80B is very similar. But I actually want to do 81 together because it's a little bit different. So let's look at 81. So question 81 says, you have a 0.185 molar solution of weak acid. And we are using the generic HA. Remember, that just means any acid. And this has a pH. So it has a pH of 2.98. And I want to know what is Ka. All right, so this is similar to question 80, except we are working backwards now. We're doing like the opposite. But let's begin with, let's start with one, write the equation with water. All right, so that's what you always want to do to start up your acid problems. So we have HA plus H2O makes H3O plus A minus. Then let's give our state symbols, AQ. You can always assume this, by the way, for this chapter. Everything's going to be AQ except water is the liquid. Ka is products over reactants, so H3O plus multiplied by A minus. That's all going to be divided by HA. So we are trying to figure out what is the value of this. And so remember, Ka is equilibrium. So these are equilibrium concentrations. However, well, let's think about this. Let's set up our ice table. We can always think about this in terms of ice tables. Initial change, equilibrium. Water, liquid, don't care. HA has an initial concentration 0.185. H3O plus is 0. A is 0. Q is 0 times 0 divided by 0.185. So Q is currently 0, so we are going to make products. So minus X plus X plus X, 0.185 minus X, X, X. So to solve this question, we need equilibrium concentrations, which mean we need X. Now, in the previous problem, let me just go back there, we plugged in our E row into Ka. That's because we knew what the value of Ka was. We could do that. Here, I don't know what the value of Ka is, so I can't do that. However, I do know what pH is. pH, which is the minus log of H3O plus concentration, is equal to 2.98. And another way I can write this is that H3O plus concentration is equal to 10 to the power of negative pH. So for us, 10 to the power of negative 2.98. That will give us H3O plus concentration. So let's do that. 10 to the power of negative 2.98. Our H3O plus concentration is 0.00147. Now I'm going to round 3 sig figs. That's what H3O plus is. So we know what H3O plus is at equilibrium. And according to our ice table, that's X. So let's start filling that in. We know what our X's are. 0.00105. 0.00105. 0.00105. X or 0.185. Well, let's do H3O plus. 0.00105. 0.00105. Now we have to find HA. That is 0.185 minus 0.00105. We bust out our calculator. 0.185 minus 0.00105. That is 0.184. That is why we say the concentrations don't really change. Because it changed by less than 1%. But we can actually calculate it. And so let's take a look at this. Oh, I wish I knew how to move you over without a touch screen, but that's okay. Let's solve for Ka. So I'm actually going to do it down here. Ka equals the concentration of equilibrium of H3O plus, which is 0.00105, multiplied by A minus 0.00105, divided by HA, 0.184. So let's do 0.00105 times 0.00105. And we're going to do divided by 0.184. Ka is 5.99 times 10 to the minus 6. So Ka is a very tiny number. And if we were doing this the opposite way, if I gave you a Ka and I asked you for pH, we could have used the excess small approximation, and we actually see why that works. At equilibrium, our concentration of acid is 0.184. So it's not a huge error if I just say it's 0.185 instead. Okay. So let's move on. Again, I know I'm moving fast on the videos, but you have the power to pause it, go back. Also, if you have questions about this, do send me an email, let me know. But let's move on to section 17.6. Percent ionization. Basically, what percentage does your acid ionize? For strong acids, we already talked about this, but that is 100%. For weak acids, that is anywhere less than 100%, not 100%. And so the equation for this is relatively straightforward. It is percent ionization is equal to concentration of ionized acid divided by initial concentration times 100%. And so if we think about the ice table, the initial is your I, the concentration of ionized acid, you can think of that as your C, your change for like HA, like how much of your acid is breaking down. So let's take a look at this. So let's do, this doesn't have a problem number. It is called together 17.6. So it's the next slide if you're following along. If you don't have your slides open, that's okay. This is actually example 17.9 from your book. So this is a book problem. We have, what is the percent ionization of 2.5 molar HNO2 if the Ka is 4.6 times 10 to the minus 4. Okay. So, as always, let's write down our equilibrium, our reaction with water. So step one, always write our reaction with water. So we have HNO2 aqueous plus H2O liquid. That would make, so An acid gives its hydrogen to the base. NO2 minus aqueous plus H3O plus liquid. Then we can write our Ka expression, product of our reactants. NO2 minus H3O plus divided by HNO2. We can set up our ice table. No liquid. The initial concentration of HNO2 is 2.5. NO2, 0. H3O plus 0. So we can calculate our Q. Q is 0 times 0 divided by 0.25, whoops, 2.5, which is 0. So we are going to make products minus X, 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 2.5 minus X, X, X. All right, there's our setup. Remember, percent ionization, we need to know what X is. How much acid broke down? That's what we're trying to figure out. We have a minus X in our equilibrium. So as always, check for the X's small approximation. So our Ka is 4.6 times 10 to the minus 4. Multiply that by 100. That's equal to 4.6 times 10 to the minus 2, or 0.046. So yeah, the X's small approximation is valid. So we can assume that the X is not going to change much. So I can ignore that, at least in the equilibrium. And let's solve for Ka. So nothing too different here. Ka is 4.6 times 10 to the minus 4. That is equal to NO2 equilibrium concentration, X, multiplied by H3O plus equilibrium concentration, X, divided by 2.5. So I need to solve for X. So multiply each side by 2.5. Let's write that down. That's 0.00115. And that's equal to X squared. So let's take the square root of that number to get X. X is 0.0339. All right. So that is how much acid broke down, 0.0339. So now I can figure out percent ionization, because that is basically H3O plus at equilibrium, or my change, divided by HA initial. So it is 0.0339 divided by 2.5. You multiply that by 100%. Remember, it's how much acid broke down, so minus X, or it's X, right? Divided by what you started with. So 0.0339 divided by 2.5. I take that number times 100. And my percent ionization is 1.36%. What this means is that 1.36% of my acid broke down. All right. And so on the slides there, let me just go to them. One sec. So if we go to the slides for what I had planned for today, I have another practice problem. So that's in your book in 17.9. You can find the solution in your textbook. Just go to chapter 17, section 6. So 17.6, and look for practice 17.9. They should have the answer there. There are other problems here where I have 0.1 molar acid, give you 2 Kas. It's the same thing though. So 82 is just more of the same. But if you're feeling like you're struggling with this concept or you just want more practice for yourself, try those out. Shoot me a picture of what they look like. Talk to your classmates. Make sure you all get the same answers. But yeah, we're going to call it there. Like I said, if you have any questions about this, this is where the end of the test is. So this ends test 3 material right here. So end test 3 material. If you have any questions about that, let me know. I will put up a homework assignment to give you more practice. But otherwise, remember, no class on Friday. I should be better than by Monday, I hope. And I will see you all in person on Monday. Take care, everybody.